Self-similar sets provide a very convenient way of constructing sets with nice structure of any dimension we choose. There's much to be said about this area and various generalizations, however, we'll just focus on one particular result that will be helpful for us in this course. Self-similar sets require a few ingredients. So first, recall that a function is a contraction with contraction ratio r strictly between 0 and 1 if it is r Lipschitz. So in other words, a contraction is a function that shrinks distances between points by at least a factor r. A set E is said to be invariant under a set of contractions if we can write it as a union of images of E under these contractions. Notice that this union is not necessarily disjoint, so these images can overlap. However, we say a set is self-similar if these images are effectively disjoint, in the sense that the intersections of the contractions of these sets have zero Hausdorff measure with respect to the dimension of the set. Self-similar sets we'll be dealing with will be defined using contractions that are also similitudes. So these are maps that are a combination of a rotation, a dilation, and a translation. It's not hard to show that given a set of contractions, there is an invariant set under these contractions. There's also the stronger result that if we look at the set function big F of k defined to be equal to the union of the contractions of a set k, then if we repeatedly apply this function f to any compact set k, then the resulting sequence of sets converges in the Hausdorff distance to this invariant set. So if you haven't seen Hausdorff distance, recall that the Hausdorff distance between two compact sets A and B is defined to be the maximum of the largest distance that any point in A can be from B, and the largest distance that any point in B can be from A. So this is a good exercise in using the contraction mapping principle and working with Hausdorff distance. We now come to the main result. So suppose we have a set E that is invariant under some contracting similitudes with contraction ratios R1 to Rn. So recall that such a set exists by the previous theorem. Furthermore, we're going to assume that these sets satisfy the open set condition, meaning that there's some open set whose image under these maps is contained in itself, and the images are disjoint from each other. Then we get that the dimension of the invariant set E satisfies the following equation. The sum of the S powers of the contractions is equal to 1. Notice that if all the contractions are equal, then this equation is a lot easier to solve. Thus, going in the reverse direction, if we want to make a set that has dimension equal to a given S, we just need to specify some contracting similitudes whose ratios satisfy this equation. Furthermore, there's a radon measure mu whose support is equal to the set E and satisfies the following inequalities. The measure of any ball centered on the set with radius at most the diameter is comparable to the radius of the ball to the power S. So notice that this is stronger than the Frostman condition. This kind of measure is called an S. Alfors regular measure, named after the mathematician Lars Alfors, who incidentally was one of the first two people to be awarded the Fields Medal. Finally, we also know that the set E is self-similar and of positive infinite measure. We provide a proof in the notes in case you're interested, which we take from Falconer's book. We'll now showcase a few common examples of self-similar sets, some of which you may have seen before. The first will be very important to us later. So this goes by a few names like the Garnett example or the Ivanov example or just the plain four-corner Cantor set. This set is made using 4 contractions, each of which has contraction ratio 1/4. So the contractions are exactly those similitudes that take the unit square, which I've drawn here, so this has side length 1, and then it takes the unit square to each of these smaller squares in the 4 corners, and each one of these has side length 1/4. Okay. So notice that these contractions satisfy the open set condition using the interior of the unit square as our open set, since the images of these sets are clearly disjoint. Repeating this process indefinitely, the resulting set looks like this over here. And using the formula on the previous slide, using the fact that the contraction ratios are all equal to 1/4, and there are exactly 4 of the ratios, the sum of the contraction ratios to the S simplifies down to just this quantity, and setting it equal to 1, it's easy to solve for S, and in this case it's equal to 1. So this is a one-dimensional, totally disconnected set. The next set is the Sierpinski gasket. So this is made using 3 contractions, each of contraction ratio 1/2. So these are exactly the similitudes that take a triangle with base length 1 and map it to 3 triangles, each now with base length 1/2 in each of the 3 corners of the original triangle. Okay, so the contractions satisfy the open set condition using the interior of this triangle. Again, the previous theorem says that if we continue this process, the intersection of our sets and our sequence will look something like this. And using the dimension formula from earlier, one can show that this set, so because each of the contraction ratios is 1/2, the sum of the s powers of the ratios simplifies to this expression. And solving for s, solving this equation for s is easy, and we just get s is equal to log 3 over log 2. The final example that we'll go over is the von Koch curve. So this was introduced originally as an example of a curve of infinite length and with no tangents anywhere. So this is formed using 4 contractions, some of which also have rotations in them. And the ratios are all 1/3. And so in particular, the contraction maps are the ones that take the unit interval. So it'll contract this by 1/3 and map, one of the contractions will contract it by 1/3 and map it to this interval. One of the contractions will map the unit interval to this line. Another will map it to this line, and another map it to this line. So notice that each one of those is a contraction or a similitude with contraction ratio 1/3, since now each one of these lines has a length of 1/3, and there are 4 of them. So because the contraction ratios are all equal to 1/3, and there are 4 of them, the sum of the s powers simplifies to this quantity here. So solving this equation results in s is equal to log 4 over log 3. And so because the dimension of this set is strictly bigger than 1, we know that the one-dimensional Hausdorff measure of this set must be infinite. So this is a curve of infinite length.